just to recap for the recording, this is a question I received from René Lohman, who said it's okay to go through his question. So first question was, he said, computing the time of pi, his laptop holds 4 cores with hyperthreading, so each core can support 2 threads. So you think the optimal computing time is obtained when using 8 processors? Well, that's a very, that's exactly what you'd think if you, I don't know if you're using Linux, for example. If you ask Linux how many processors I have, it would say 8. But actually, it's 4 physical processors with 2 hyperthreads each. You get the optimal time at 5 to 7. Okay, so so first of all, I would have said that the actual optimal time for this program on your machine would have been on 4. Now, the reason for that is that hyperthreading allows 2 threads to run at the same time on the same physical CPU. Okay. However, they have to share the resources of the CPU. And here you're doing a floating point calculation. Although you have 8 hyperthreads, you only have 4 physical floating point units. You have 4 physical processors, each with its own floating point unit. And so actually, these the 2 processors, let's assume the operating system gives, with 8, say, gives 2 processes to each physical CPU. Those 2 processors are sharing the same floating point unit, and because you're doing nothing but floating point calculations here, they're just having to queue up for each other, so you don't get any benefit of hyperthreading. Hyperthreading is unfortunately not any use for high performance computing, because it's useful if you were running a compilation, which is, say, largely integer arithmetic, and doing an MPI program, which was largely floating point at the same time, that they could run together. But because you only have 4 physical CPUs, you only have, I would expect the optimal to be at 4. Now, the reason why the optimal is more than 4 sometimes is often, maybe that you say this here, is that let's see. So you get some benefit, but the other thing is that the other time you get programs going faster beyond the number of physical processors you have is that your computer is doing other things. Okay, so if your computer is doing something very heavyweight, it's going to have to take some time to do that. So if you run 3 MPI processors, yeah, well, what happens is you get better scalability through sheer weight of numbers. The more MPI processors you run, the operating system gives them kind of a fair share, and they just crowd out the other processes. So there's 2 effects here. One is you're not going to expect to get much performance beyond the number of physical CPU cores. But secondly, if you're doing other stuff, the more processes you run, they just get more of their more share of whatever resources there are. So you can get some improvement beyond the 4. Does that answer the question? The second question is about ping pong. Again, very interesting observation. If he sets, if he does a ping pong with 100 million iterations and 800 byte messages, I get a runtime of about 2 minutes, 2.5 minutes, with a bandwidth of ½ gigabyte. But if I increase the number of iterations by 1,000 and increase the message size by 1,000, I obtain 8 gigabytes. So the reason for that is, yes, it's simply a matter of meta information that's sent to high numbers when the message size is small, iteration number is high, and that's exactly true. So when you send a message, sending any message requires an overhead, and often it can be a software overhead. You have to send something, and so this is typically called the latency. And on your own laptop, this will be small, but the latency will be in the order of maybe ½ a microsecond. So for any message you send, any message, yeah, you're going to spend about, let's say, ½ a microsecond, I'm guessing here, sending that message. Now, that means that when you send an 800 bytes is a very small message. When you send an 800 byte message, it will be dominated by the latency, okay? Absolutely dominated by the latency. In fact, we can probably guess here that if you're doing 150 seconds for you're doing 1.5 seconds for a million iterations, which would make me think that the latency is about a microsecond, which is sort of in the ballpark I'd expect. I mean, you've got so it looks like your latency is about a microsecond. So when you're running small messages, then you when you're sending small messages, then it's dominated by the latency. But when you send large messages, that just gets that becomes irrelevant, and you see the bandwidth. So to measure the true bandwidth, you need to send large messages. If you want to measure the latency, you do actually want to send small messages. So I would guess on your system, the latency is about a microsecond, and the bandwidth is what you get, 8 gigabytes per second. A very, very useful figure is some people call it n.5. It's the message size at which you spend half your time sending the message and half the time in the latency. So for example, if we assume that the latency is about a microsecond here, and you're doing 8 gigabytes per second, that would mean that actually that the messages below about 10 kilobytes are dominated by the latency. That, you know, if you're sending a message smaller than 10 kilobytes, it's actually spending more time just setting things up than it is sending the data. So often people ask, what's a small message and a large message in MPI? Well, it depends on the system, but a good definition is the MPI message size at which you spend as much time doing the setup and overhead, the latency, as you do sending the message. And that is often in maybe a few kilobytes, maybe 10 kilobytes. So does that answer that question? Is that useful? They're a very good question. So what I was going to do now is switch to the quiz. So I'll hopefully, if I reshare the just briefly, if you could all go to, it's difficult, I can't show more than one thing at once, but hopefully. So we're going to do this, use this Socrative quizzing system. I see about 10 of you are logged on, but if people could go to www.socrative.com and log in using the student login and enter HPC quiz as the room name. So we have about 20 people on the, but there's only about 10 people in the, so people could do, I'll give you a few minutes to do that. The first question is clearly just to get things, going. It's just, we use this quizzing system in the first day of the course, but just to get information from you. I didn't. Okay, so the first question, I can see most people are logged in. If you could just select your answer and almost every, okay, so how did we do? So it's the message passing interface, but it's also a way of doing distributed memory parallel programming. So the explanation is some of the questions have more than one answer. So there were two reasons for this question here. One is to just get you logged on, but also to show you that there are multiple answers to some of the questions. So some of them do. So just be aware of that. So the next question is, so I would just say that this quiz is to try and explore what we've learned. None of the answers to any of the questions are stupid. All the answers could have been true for some message passing system in the past. Okay, if you don't know, just guess. It's all anonymous. I don't know who you are, and we can discuss the answers. But don't, you know, if you get the wrong answer, don't worry, because none of these answers are stupid. They're all perfectly reasonable answers for a particular. If I said to you to compile and run a message passing program requires these 4 options, they could all be true. However, for MPI, which we're learning about, some of them are true and some of them are not true. But it's very important to realize that none of the answers to any of these questions are stupid. Sorry, they're all perfectly sensible answers to the question. In general, it just means that for MPI, MPI has a particular choice. And so if people could, yeah, most people have answered. People just have a guess. Okay, I can now. Okay, that's fine. So everyone, some people said special compilers. Now that's a perfectly reasonable answer because you know, when you compile an MPI program, you type MPI F90, MPI CC, MPI CXX. However, that's just a convenience. These MPI commands, MPI CC, MPI F90, are just wrappers. They're just convenient ways of launching what is actually a normal compiler like GCC, Intel, or Cray. And as it says in the explanation here, it sets up the link paths and such like. But so actually there is no such thing as an MPI compiler. MPI is not a language, although the way it's presented to you does make it look that way. So you know, A is a perfectly reasonable answer. It just happens technically not to be correct. You don't need a special parallel computer because all you actually need is to be able to run multiple processes, and you can run multiple processes on a single CPU. And in fact, any modern operating system for the past 20 years has been able to manage multiple processes on a single CPU. Okay, so the next one. After initiating an MPI program with MPI run -n for /my MPI program, what does the call to MPI init do? So as I said, if you don't know, just guess, just pick what you think is the most reasonable answer. It's all anonymous. I'll maybe click how do we do when we've had a bit more than 3/4. Okay, most people have answered that. Okay, so it doesn't create the 4 parallel processes. Now, you know, there are message passing, there are parallel systems, and there have been message passing systems where that happened. There used to be a system called PVM, Parallel Virtual Machine, which did that. But it doesn't. MPI, when you do the MPI run or MPI exec or whatever your job launcher is, at that point you create multiple processes, and we demonstrated that by, if I did a print statement before MPI init, I got multiple prints and multiple hello worlds. It doesn't start program execution. Remember, this is the library, so actually you have to start the execution in the normal way. So what MPI run -n4 does is it just runs 4 copies of the program, my MPI program, just runs them. Okay, that's all it does. However, once you call MPI init, they get together and it enables the 4 independent programs subsequently to communicate with each other. As I think I demonstrated on the first day, I don't know if you're all here, but I can MPI run the ls command. Okay, I can MPI run any command. It just launches that many, launches multiple copies. So the next question is, if I call MPI receive and there's no incoming message, what happens? And again, different message passing systems have taken different approaches to this in the past, but MPI has a particular approach which we can discuss. Okay, so most people have answered. Okay, so you did so. Actually, most people got the right answer. The receive waits till the message arrives, potentially waiting forever. The receive doesn't report there's no incoming message, and the reason is there are no timeouts in MPI. So that might surprise you. But actually, MPI assumes that the hardware is 100% reliable and that your program is correct. So it assumes that, you know, if you issue a receive, then there will be an incoming message. Now, you could imagine this, that means that MPI is not fault tolerant, because, you know, if there were a hardware or software fault, not a program fault, but an operating system or hardware fault, you could issue a receive. You've written a program where the send should come in and that process is dead or stalled or gone away. But MPI, there has been a lot of talk about putting fault tolerance into MPI for many years, but MPI is not fault tolerant. It basically assumes that the hardware is 100% reliable and that your program is correct. And if you are operating in an environment where networks are unreliable or resources are coming and going, if you wanted to run across a cluster of workstations where someone might come in the morning and reboot one of the workstations, you can't use MPI currently. The next one is, we're going to talk about send. If you call MPI synchronous send, MPI send, there's no receive posted, which are the following. Now, I see most people are getting, don't worry if you're not getting the right answers, but I said a lot of people are getting the right answers. So clearly people have been following the course quite closely. So I say, which of these are possible outcomes? So again, I'm trying to be slightly, so people are very, sometimes this quiz takes a long time because people are reluctant to. It's probably in a classroom setting, people are more reluctant to have a guess, but that's very good. Okay, fine. So the correct answer is the send waits until a receive is posted. Now, there are ways in which the message could be stored and delivered later on if possible in MPI, but that's not synchronous send. So the message doesn't appear, the message doesn't fail with an error and it doesn't time out. Okay. The send waits until the receiver is posted, potentially waiting forever. Again, assuming that the hardware, the assumption being the hardware is 100% reliable, and that you have written the correct program. So synchronous send is like making a phone call. There are no timeouts. Okay, so that again may not be what you expected, but so actually, okay. So remember, in MPI we covered. I mean, I concentrated on MPI Send because its behavior is clear here. It's like making a phone call. But I did mention that there were other. So for example, if you call MPI asynchronous send, MPI B send, buffer send, and there's no receive posted, which is the following are possible outcomes. I'll see, how did we do? Okay, so now the message disappears. That's actually, so that's sort of that could, I mean, yeah, the message might not. That's a very good. I think the message disappears is probably not the right answer. What I mean here is if at any time in the future a receive is posted, then the message will be delivered. So that's but most people got the important points, DNF. The message is stored and delivered later on if possible. But also the sending process continues execution regardless of whether the message is received. And so, you know, DNF are the two things which mean it's like sending a letter. You put the letter in the post box, or you send an email, and then you carry on. Now, when I first set this question, someone stuck their hand up and said, isn't B a possible answer? And actually, if you look down the left-hand side, this indicates which are the right and the wrong answers. Actually, the send can fail with an error. Now, this is a slight technicality, but I didn't even pick this up the first. But actually, this can happen. So it is a possible outcome that when you issue a buffered send, the send fails with an error. Can anyone remember why that might happen? Under what situation that could happen? Not enough buffer. And why might there not enough buffer? I mean, you're absolutely right. That's exactly the right answer. No, exactly. Okay, they're all correct. So important point is what, yeah, exactly what Michael said there. We've either not assigned enough. So the strange thing about MPI is that to do these asynchronous sends, these buffered sends, it's up to the user to assign MPI the buffer space. Okay, so you have to call this strange routine called MPI Buffer Attached. And if you have not assigned any or enough memory, as someone said here, there's more. As Laurent said, there's other B sends pending. That can run out. So if you issue synchronous send, then you wait forever. If you issue buffered send, you hope it's stored and delivered later on if possible, and you carry on. But actually, you could fail with an error. So there are 3 B, D, and F. And if you note, these are you allowed to overwrite the buffer? I don't quite know what you mean there, Michael. So it is quite subtle the way bsend works, which is one of the reasons I don't cover it. Could you? Oh, okay. So well, the model is that you call MPI Buffer Attached at the start of your program. You say to MPI, here's a megabyte of memory. I want you to use it for buffered sends, and you just, that's then for MPI to use. MPI will manage that. And so it will manage it, and it will use it, you know, when sends. So yes, if you issue, so it's not really you overwriting the buffer, but MPI will reuse that memory. So if you give MPI a megabyte of storage, hopefully if there's never more than a megabyte of outstanding B sends, you'll be okay, because MPI will manage that memory and free it and reuse it as required. So it's not for you to use, it's for MPI to use. Does that make sense? I don't know if that was your question, Michael. Yeah. So if there's no receive, well, no. So if there's no receive for a B send, no. Basically, it will just, because MPI won't. No, MPI said, well, there's no receive, but you might post the receive right at the end of the program. So MPI never drops them. So MPI doesn't drop messages. It either bombs out, or it, you know, so it delivers them. So no, it doesn't release them. You know, it will just sit there forever, basically, because MPI doesn't know you're not going to issue a receive in an hour, 10 hours, a year's time. I had a slight caveat there. There is an MPI routine called MPI Send, which basically tries to send the message, and if there's no receive posted, it disappears. It's a fire and forget. And for those who are networking, I'm not a networking person, but it's like is it UDP rather than TCP/IP? It's anyway. It's there for historical reasons, and you would never use it. Okay, there are situations in reality where you would want that. If I'm streaming a movie or maybe a phone call to, if I'm streaming a movie, maybe a bad example. If I'm streaming a live TV event, okay, a football match, to my home TV. If messages start getting dropped, okay, if the network is slow, I want frames just to disappear. I want it to catch up. Yeah. So if there's in that situation for streaming live TV, if there's no receive posted, you know, then you just want to drop the message and catch up. So there are situations where if you send the message, send data, and the receiver isn't ready, there are situations where you just want to get rid of it because there's no point and it's too late. However, that is not true for scientific and technical. Yes, it is. I didn't know the technical term. It's UDP versus TCP. So there are situations where that's a useful behavior, but not in scientific and technical programming, and that is what MPI is designed for. And so it's not a use case which is useful. So RSend is there for historical reasons. I've dropped it from the course because it should never be used. Okay, so let's go. There's the explanation. It's basically what I said. So you'll notice that the A, B, C, D, E, F were the same options for synchronous send and B send. And now you'll ask the obvious question, but if you call a standard send MPI send and there's no matching receive, which of the following are possible outcomes? And remember, I recommended that in real programs, you should program with standard send because MPI, well, you should, but for developing programs, when you develop them, you should program with synchronous send because we know exactly what it does. So this is none of the questions are easy, but this particularly isn't an easy one. Okay. So MPI send can decide to be synchronous send or standard send. Or sorry, can decide to be synchronous or asynchronous. So given that the correct answer for synchronous was C, and the correct answer for asynchronous i.e. buffer send was B, D, and F, you would expect that the correct answer for this question were B, C, D, and F, which is what some of you have put. However, that's not true. So you're absolutely right. If MPI decides that it's going to be synchronous, then C is the correct answer. If MPI decides it's going to be asynchronous, then D and F are the correct answers. However, B is not a possible answer. So why is B not a possible? Now B was a possible answer for explicit buffered send. Why is it not a possible answer here? Why? Maybe somebody could just. It's not an easy question at all, but yes, so exactly, Lee and Laura, absolutely. So the point about MPI send is it's trying to give you the best of both worlds. And so if you do MPI B send and there's not enough buffer space, this is buffer space you have given MPI, it will fail because MPI says, you've asked me to do a B send, you've asked me to store this message, I can't. However, the whole point about MPI send is it's trying to give you the best of both worlds, but without this failure. So if MPI B send, as Laura and Lee have pointed out, if MPI send decides there's not enough buffer space, it will say, well, I can't buffer it, but rather than failing, I have the freedom now to become synchronous. And so MPI send gives you the advantages potentially of B send and S send, but without the disadvantage of B. Is that clear? So it is a slight subtlety, and it's actually something I didn't understand for many years, several years. But luckily, when I first started working at EPCC, there were people at EPCC who were developing MPI implementations actually for the Cray T3D, which was our machine in the mid to late 90s, and I could just go and ask them. I could ask, like, I don't understand this, could you tell me what's going on? And they were able to tell me. So the next question is, the MPI receive routine has a parameter. What does this mean? Now, let's just, I think somebody's just come to my door. Apologies. I'll take a quick break. I'll just be a minute or so. Okay, so how did we do? Okay, so this is actually, you would think B is really the obvious answer, the size of the incoming message, but actually the correct answer is D. Is the size of the buffer view of so the important point is almost everyone got it right that you don't specify sizes in bytes. MPI tries to avoid talking about bytes for a number of reasons. The main reason is for portability. You know, bytes isn't a portable. You know, an integer could be 4 bytes on one machine and 8 bytes on another. So you do it in items. But actually, it's slightly strange. But when you specify a receive, you're not saying the size of the incoming message. You're saying I would like to receive a message, and I have reserved this much space, 10 integers, for the incoming message. So now, often in many programs, that is, I admit, the size of the incoming message. Okay, like in your ping pong example, you know that if you're pinging around 1,000 integers, then if you have 1,000 integers receive buffer, the send is going to be 1,000 integers. But technically, it is actually the MPI allows you to receive messages of unknown size, and which is a useful thing to do. And so the receive is saying, I'd like to receive a message, and by the way, this is how much space I have reserved for that incoming message. So the obvious next question is, what happens if the incoming message is too large? So I'll come back to that, Laurent. That's a very good question. That's actually probably going to be covered. So what happens if the incoming message is larger than count? And again, this behavior is not obvious. If I'd asked you to write the message passing library, you might have made, some of you might have said A, B, C, or D. Okay, they're all reasonable things to do in general, but MPI has a particular choice here. Okay, so actually, and it's obviously an unusual thing, people didn't expect, the receive fails with an error. Okay, so I mean, why? Well, basically MPI is very MPI is very risk averse, and basically it's saying you've sent me a message that I can't receive. Okay, I'm not going to do C. I'm not going to write beyond the end available storage, because that would be that could corrupt data. So then your program would carry on running, but with corrupted data. So the reason you tell MPI how big your buffer is when you issue a receive is so that you don't corrupt data. You could receive only the first count items. Okay, you could receive zero. You could report 0 data received, or you could receive the first count items. But then it's not clear what you would do. Okay, and if you did D, there'd be a real risk. You've said, I'd like to receive a message from you. I've got 1,000 integers, and you receive 1,000 integers, but the sender sent 2,000. What happens to the remaining 1,000? MPI's model isn't like a pipe, data in, data out. MPI works on matching individual sends to individual receives. So although you could do B, C, or D, it's not clear what you would then do. I mean, as a programmer, you want to know if the incoming message is bigger than the buffer you have allocated, then you have a problem. Okay, and so MPI says, look, I'm just going to say I can't do that. Okay, and so it's really because it's not clear what you would do to continue running correctly if B, C, and D, if you did it B, C, or D. Don't know if that's obvious, but anyway, A is the correct answer. It's one of the few times you get a sensible error message from MPI. When it crashes, it says incoming message too large, or something like that, or incoming message truncated. But it truncates the message, but it fails. So I think the next question might go some way to addressing what Laurent said. He said, on the send side, does the status tell what is the size has been received? Let's see. Okay. So what happens if the incoming message size n is smaller than count? Okay. So you've issued a receive. You have said, I've got count integers. The incoming message is of size n integers, and it's smaller than count. Okay. So actually, it's not this question, it's the one after, which might address what Laurent wanted to know. So I'll see how he did. So, the reason why A isn't the right answer is that MPI is trying to allow you to write programs where you don't know how big the message coming in is. So now, you might have the assumption is you have an upper bound. You can say, look, you're going to send me a message. I don't know how big it is, but I've reserved lots of space. Okay, so MPI wants you to be able to write programs where the incoming message size is not known, and that's why A is not the right answer here. And so the first 10 items are received, that's C and D. So most people got that correct, although it's not immediately obvious. Now, the reason the rest of the storage isn't zeroed, I think there's two reasons here. First of all, you might not want that. You might have an incoming buffer where, I think the real reason is that MPI is written for efficiency. Okay, so if I issued a receive and I said, look, I want you to send me a message. I want to receive a message from you, and I've received a gigabyte, and you received 1 byte, okay, you'd be a bit annoyed if MPI went away and spent 10 seconds zeroing the other 999,999, or however many bytes, okay? So actually accessing memory is cripplingly slow on modern computers, unfortunately. And so it's really for efficiency. There's no point zeroing the rest of the storage. That would take time, and MPI is written for efficiency, so it doesn't do that. So as I said in the explanation, you may know the size of one message, any count might be the same. However, you might not know how many items are being sent. So for example, if you're doing a simulation where you were a crowd simulation, where you had people milling around, and you divided the domain up into a grid, and every time step people could obviously move, people could leave the domain of one process and go to another, you would say, look, these 7 people have left my domain, they've moved into your domain, could you take control of them? You'll be exchanging data across boundaries, but you don't know how many people are going to move. So when you do the receive, you think, okay, I'm going to get data from this, I'm going to receive from my neighbor all the people that have moved into my domain, but that could be 0, it could be 100, okay? So you have to reserve a large amount of space. And then, so the question here is, if you issue a receive with count, the receive completes, so you know a message has come in, you know the incoming message was of size less than or equal to count, but how do you know how big the actual message is? Now, often you know, in some programs you know because in a ping pong, you wrote the code, you're sending 1,000 and receiving 1,000. But in general, when a receive complete, you know is that a message has come in where the size was smaller than the buffer. This is one of the cases where it's stored in the status parameter. So now A can't, well, if you're a Fortran programmer, A could be true. If you're a C programmer, then actually the value of count can't be updated. If you look at the prototype, it's passed as an integer, not a pointer. So actually, it's not possible for MPI. In Fortran, because Fortran always passes by reference, it could be up, but it's not. Okay, it isn't. It's reported. If MPI couldn't tell you, then that would be difficult, because then it would be hard to write general programs with messages of non-determined size. Because when you receive a message, if it's of indeterminate size, you do need to know how big it is. You could pass the size via the tag. You could do that. You could choose to tag all messages with their size, but actually that's not. The tag is a general thing which you can use for any purpose. It's actually the status parameter. So when you receive a message, the data goes into the receive buffer, which is of size count, and the metadata, which is where it came from, what the tag was, and actually the associated tag. The tag is actually stored in the status parameter. So even if it were via the associated tag, you access that via the status parameter. So when a receive completes, the status is updated, and you can then say, what was the tag, and in particular, what was the size of the message through you have to pass it to a function called MPI get count, but it is available via the status parameter. Now, Laurent asked, on the send side, does the status tell what the size has been received? It's only on the receive side. On the send side, there is no status. So on the send side, if the send completes, then well, if it's synchronous send, then you know that it has been received and that all the data has been received. If it's asynchronous send, i.e. either be send or potentially send, then you don't know if it's been received. Does that answer your question? So the send, so it's only actually, there is no status on the send, it's only on the receive. So the receive does that. Okay, so the explanation is, so the only problem with MPI about the site is not available by direction, you must pass the status to the helper routine MPI get count, which is slightly awkward, but so a couple of questions which I added recently. Which of the following are possible outputs from this piece of code run on 3 processes? Okay, so I say possible output, I'm not saying, but some of these are possible and some of them are not possible outputs. I put this question in because output to the screen, I mean, in real MPI programs, large scale, you're running via some batch system on thousands of processes. But of course, when you're debugging, you're running on your laptop or on the front end login node, and it can be confused. The way that the messages appear on the screen can be confused. It's not as useful as you might think. So most people have answered. So I'll just maybe wait for one more person to have a stab. Strangely, Socrative allows you to answer after I've done how did we do, so it could be a bit confusing, but if one more person maybe just wants to take a guess. Okay, fine. So so A, C, and D are all correct. Now, the way I explained it is that you have output from one process and output from another process, and within the output from a particular process will be in order, but they can be interleaved in any way. And so you could get any order here where the goodbye from a rank comes after the welcome. So in A, all the goodbyes come off, that's fine. In C, for rank 2, it is true, welcome, goodbye. Yeah, for D, but for B, we can see that the goodbye from rank 1 happens before the welcome from rank 1. So B is not possible. Okay, so that was just to make you think about this. That and people did very well on that. It's not an easy question. That is that, do people understand that? Sorry, is that clear to people? The important point is that it's actually quite remarkable that all the output appears on the screen, because you've got multiple processes running, but actually they're all mediated by the when you launch a program using MPI run, what probably happens is the MPI run program launches these processes, but still keeps in touch with them, and in particular collates all their standard outputs. And so the MPI run program is there collating the outputs, and it can make sure that they're not interleaved on a character by character basis, in which case the prints. Now, sometimes I have to say I have seen it occasionally. If you run on vast numbers of processes, then sometimes it can go wrong and you get lines mixed up. It's rare, but in general, you'd expect output from a particular line not to be interleaved, but that line by line the interleaving can happen in any way. So there's an explanation here. I've just said all that. So the next question, which is the second last one, is so this is a slightly subjective, but I do see people writing code where they loop for I equals not I, they loop over processes, and this is, now you sometimes do that. Okay, in the Pi example, you looped over processes because the master was sending data, but sometimes people do stuff like this. More people think, again, this is not an easy question. I put it in because it was something which I wanted to explore in the course. One more person take a guess, and then I'll see how we did. Or maybe we'll just have people maybe. Okay, well, so we'll look at the answers. Okay, so D. Now, actually, I've written this slightly wrong, because actually the first time but D would only be true if J were a shared variable across processes. Okay, so the idea of D is not correct. D would be, well, actually, I've got my arithmetic slightly wrong here. I need to update this because actually on the first iteration, imagine J, now this is not possible in MPI. Imagine J were a shared variable across processes. It would actually equal to 0 because rank 0 would multiply it by 10 times 0. So I've got my arithmetic slightly wrong. But D could only be true, or something like D could only be true, if J were shared. So J is not shared. In MPI, all the processes all the variables are private to a process. So A is not true. Why is A not true? This loop does not ensure the operations are done in order. Okay. Why is that A not true? All processes execute the for, yes, but that's absolutely true. But also, there's no actually, all process, but process 0 could execute the for loop, and process 1 might be 5 minutes away, or process 1 could have executed 5 minutes beforehand. There's no synchronization between processes here. You're absolutely right. All processes execute the for, but as well as that, you have no control over the speed of the processes. There's no synchronization in that loop. There's no barrier or anything, and so you don't know. Process 0 could execute the for after a minute, and process 1 might be 10 minutes down the line executing it. So this is not an easy question. Most people have got it right. The loop is entirely redundant. This is equivalent to me saying to all of you guys, okay, everybody count from 1 to 100 in your head, and when you reach your age, say hello, okay? Right? So you go 1, 2, 3, 4. I get to 54. I say hello, okay? That loop is entirely redundant, okay? It's entirely redundant loop. You're all just looping. There is only one place where rank equals I. There is only one point in that sequence of counting from 0 to 100 where the number reaches your age. So sometimes people have the wrong mental model about MPI, and they think that this in some sense loops over processes, or it doesn't, okay? This is entirely equivalent to everybody doing print hello from rank blah, J equals 10 times rank. Okay, so every time you find if you ever start writing loops across processes with if statements, then you have to think to yourself. Now there are places where they are required. Okay, you might be sending a message to each process, but in general in MPI, and the reason that the loop does not ensure their operations are done in parallel, and that's good, nobody said that, is that everything is done in parallel in MPI. Okay, it's the difficulty in MPI is getting things done in serial, not getting them done in parallel. Okay. So is that clear for people? Okay, that unfortunately it does not ensure A because there is no synchronization here, and D is not true because J is not a shared variable. And I need to update the logic here. That is slightly incorrect. But okay, so the final question now apologies that I know that actually most people on this course are Fortran programmers, but I did this code in C, because normally most people are C programs, but hopefully it's really quite clear that basically we have a loop here, and if rank %2 equals 0 in C, that's the mod operator for Fortran. So the even processes execute the first branch, and the odd processes execute the second branch. Okay, and as the comment says, okay, and we have so the reduction operation is passing in if you're a Fortran programmer, you can ignore the ampersands. You're passing in the rank and getting the result of the all reduction into the even sum, and you're summing one MPI int. So you're adding up, and so so this reduces passing in the rank and putting the result in either even sum in the even processes or odd sum in the odd processes. Okay. So if I'm running on ranks 0, 1, 2, 3, 4, 5, 6, and 7, what is the correct answer here? Just wait for a couple of people to get the answer. Just take a guess if you don't know. Not a problem. Okay, so how did we do? Now, apologies, this is the closest thing I have to a trick question. So the code is, the program is written to make it look like the answer is C, okay? And I think whoever did A has just got the evens and the odd side the wrong way. That could be a Fortran C thing, a 1-0 thing. But basically, the code is written to trick you. This is the only trick question here. So, but the answer is actually B. Could someone who answered B tell me why the answer is B in the? Yes, both are on ComWorld. Yeah. So absolutely. So the code is written to make it look like the first reduce and the second reduce are different, but they're not. The point is that they're actually calling, they're all across ComWorld. And so actually, as I've put the explanation here, although the reduction operation is called from different lines by different processes, they're all participating in the same reduction operation because you're passing ComWorld. As a result, every process computes the sum of all the ranks, 28. The only issue here is that all the if statement achieves is that rank 0, the even ranks put that sum into even sum, the odd ranks into odd sum, okay? You might think it's strange that two reduction operations called from different lines of code can match each other, but actually MPI is a library, so it has no idea where you're calling these from. All it knows is on each process, David's called MPI or reduce, he's passed MPI ComWorld, that means I have to wait for everybody to call it, and then we'll all add up our numbers. And so although in most programs, the way you write them, typically a reduction operation will be called from the same line on every process, that's not a requirement. And in fact, MPI couldn't check that. And as Michael said here, that the reason it doesn't work if you've not instantiated two separate communication worlds, if you wanted to do what this code purports to be doing, you would have to create an even communicator and an odd communicator using MPI com split, and then call the reduction operation on MPI com odd even or whatever you want to call it. So is that clear to everyone? It is a trick question. I was actually, I mean, don't feel bad if you got it wrong, because it is a trick question, but it does illustrate an important point. If MPI were a compiler, it could have different behavior. It could say, oh, okay, well, you know, I want these to be different because David's calling them from different lines, but MPI as a library doesn't even know where they're called from. So I can actually look at, this is all anonymous. I don't quite understand the how these answers work, I have to say. I've never really let's see if I can. No, okay. I'm just playing around here. I'm not doing very well, but okay. I just wanted to see how people did. But anyway, so we you know, quick question of the class. I don't quite, what I'd like to see is, you know, oh no, sorry, apologies. This is the score by person. Okay, so some people did, you know, there was some, I mean, they're not easy questions, but some people did really well, so it's up to you. I don't want that. So, okay, so hopefully that was useful. I will try and put up a copy of this quiz on the website. Obviously, you can watch the video, but that's rather laborious. I think I can export this as a PDF. I will try and do that and put it up, because I know people want to look at it back, and if I should be able to produce a PDF which has the questions also indicating the right answers, and also with the comments, the explanations in there. So hopefully that would be useful for some kind of revision. So what I was going to do now on the following the timetable is to introduce the case study. The case study is the closest thing I have to a real program on the course. It might take a bit of motivating, and it draws together, allows you to put together what you've learned to write what is the closest thing I can imagine to something which is sort of a real program. So I'll just get set up for that. Fine. Okay, so we should be able to be okay. So just before I go on to this talk, are there any questions that people have that came up from that quiz, or any questions at all at the moment? If not, I'll just carry on with this, and there's going to be a chance later on to answer questions both collectively or individually. Okay, so this is an example I came up with a while back on. I'm just trying to. Okay, so hopefully you should be able to see. Yeah. So a case study for domain decomposed MPI code. So what I'm going to do is there's a short lecture, then I will basically there's quite an extensive exercise sheet, and I'll point out the salient points in the exercise sheet, and then you can go and work on it. So what we're going to do is we're going to do an image processing example. It's slightly contrived, but hopefully it's quite fun. So we start with a big array, and this array in the program we're going to write is actually going to correspond to the pixels of an image, a moderate sized image, a few hundred by a few hundred pixels. We want to process that array, and the classic thing we do in parallel, as we illustrated when we looked at the conceptual exercise in the very first day of the traffic model, is we split it into pieces. This is domain decomposition, okay? Exactly as we did with the traffic model. Now, the difference with the traffic model is that we had a line, so each process only got a line. Here we are decomposing into slices, so each process gets a 2D array. Now you could say, why have you decomposed into slices? Why haven't you decomposed into 4 pieces? Well, we'll come back to that. But actually, it's much more simple if you decompose the domain in a 1D decomposition, i.e. decompose it into slices rather than into a grid. We can discuss why that is later. You assign the pieces to processes, so process 0, for example, has this part, process 1 has this part, process 2 has this part. But it turns out that the way we're going to we're going to do an edge detection, or an analog of an edge detection algorithm. And it's going to turn out we're going to have to compare each pixel to its 4 neighbors. Again, just like in the traffic model, we had to compare the value of each cell to its 2 neighbors in 1 dimension. In 2 dimensions, the equation or the update rules we're going to use are going to require comparing a pixel to its 4 neighbors. So you need to know what the values of the neighbors are. And just like in the traffic model, clearly at the boundaries you have a problem, because if I'm here, I know the boundary value is here, but I don't know what the value of the neighboring pixel is here. Its value because it's stored in this process. And likewise, this process too, if it wants to know the value of a pixel down, it's down here on a different process. So what we're going to do is we're going to add halos to deal with these nearest neighbor interactions. Exactly analogous to the traffic model, which is why I introduced the traffic model, because hopefully it's an analogy for this more, at least from the communications side, it maps onto this more complicated program. The difference here is that the halos are entire lines of pixels, not single values. So when you do halo swapping, this data here, the extreme data from this process 1 will be placed in the halo of process 2, and this lower boundary of process will be placed into the halo of process 1. And that's identical to the halo swapping that took place in the traffic model. You send a message up to your neighbor, receive. You send a message down to your neighbor, down, receive. Except the data you send is an entire line of pixels. And actually, it's completely analogous to the communications pattern we used in the message round a ring example, where you send and receive messages. Except here, this is in the message round a ring, we send a message up and receive down. Here, we also have to send down and receive up. But they're all basically the same thing. So what we're going to do is imagine we have an edge detection algorithm. So here's a picture of William Wallace. It's actually Mel Gibson playing William Wallace. He did something, I've actually not seen the film Braveheart, and I guess a lot of people will have seen it. He did something which makes you very popular in Scotland, apologies, which is to kill lots of English people. Apologies, actually I'm English, so I can say that. So he's very popular in Scotland because in when was it? No, 1300 something, he killed lots of English people, and then he came to a sticky end himself. Anyway, we're going to do an edge detection algorithm, and so you can do an edge detection, and I'm going to present you with a very, very simple edge detection algorithm, which can produce you this picture on the right. Now, what I could ask you to do is to take that edge detection algorithm and parallelize it. So to take a picture of Mel Gibson, I'm not going to give you a picture of Mel Gibson, I'll give you some other pictures, and do an edge detection. Now that's not a bad answer here, actually. Actually, that's a single pass. We can do a single pass through the image and get the edges. We could parallelize it, but what you're going to have to do is you're going to have to read in the image, distribute it to all the processes using some kind of scatter, maybe do some halo swapping, excuse me, detect the edges, reconstruct the image on a master process through a gather and write it out. The I/O, all the messing around is going to, so it would not be worth parallelizing the edge detection algorithm because it's just not enough computation. because it's a single pass. What I'm going to do, which is slightly fake, is I'm going to give you the edges and you're going to have to reconstruct the image. It's a slightly fake thing to do, but hopefully it's quite fun. And that takes hundreds of iterations, hundreds and hundreds of passes through the image. And that's why it's, although it's a slightly contrived thing to do, that's why I ask you to parallelize this, because it is worth parallelizing. So edge detection probably isn't worth parallelizing, but inverse edge detection is worth parallelizing because it takes hundreds of iterations. So the edge detection I'm going to do is a very, very simple one. You compare the pixel to its 4 nearest neighbors. So let's say the pixel values between 0 and 255, where 0 is black and 255 is white. That's what we'll do. You set the edge value to be the difference between the image, the value in your neighbors, which is the pixel to the right, up, left, and down, minus 4 times their own value. What you're doing here is you're computing the difference between the value of your pixel and the average of the 4 neighbors. So if pixel ij has the same value of its 4 neighbors, this edge value is 0. And so if a pixel is the same value as its 4 neighbors, nothing's happening, there's no edge. However, if a pixel value is very different from its 4 neighbors, you get a large edge value, okay? So it's not obvious, but this is a very naive but reason. You can see why it might work. If I set the edge value to be the difference between a pixel and the average of its 4 neighbors, that might do something. And actually, whoops, this is what I've done here, and it gets a surprisingly good answer. Actually, I mean, it's not brilliant, but it's not bad. What about the boundary conditions? You might say, well, what happens? What's the neighbor of this pixel up the way, the neighbor of this pixel to the right? Well, unlike the traffic model, it doesn't make sense to have periodic boundaries here. So what I'm going to assume is that Mel Gibson, the picture is embedded in a sea of white, which it is here. And so if I look up, right, left, or down off the image, I get pixels off the edge of the image are set to white. So image M, if the image is M by N, image M plus 1J is set to white. So what we're going to do is in the serial code, we're going to actually pad the 2D array with halos, and all halo values are set to 255. So even the serial code will have a halo of white pixels. So we're embedding the image in a background of white, just as the picture shows here. Okay. So is that clear what the edge detection is? It's a very, very simple. Compute the difference between a pixel and the average of its 4 neighbors modulo some factor of 4, and that gives you the edge value. Okay. Okay. Now, actually, it's not immediately clear, but given this simple algorithm, we can actually there's enough information in the edges to reconstruct the image, and we do that using something called the Jacobi solver. Now, if you've not got a mathematical or scientific background, you can ignore this. But some of you may have recognized that that is the formula for a 2D second derivative. This is saying edge is grad squared image. Okay. And that's actually saying let's call the edge values the second derivative of the image. So if the image is flat or changing linearly, it's not an edge. But if the image has a grade, it has a curve either up or down. If there's a finite second derivative, then we'll call that an edge. So actually, I'm solving grad squared image equals edge. Okay, edge is grad squared image. I want to solve grad squared image equals edge. So we're actually solving a Poisson equation here. Now, if you don't have a scientific technical, it doesn't matter. All I'm telling you, you have to trust me here, is that if you apply this equation many times, okay, you will recover the correct image. So we make an initial guess to the image, which I've called old, and we can just guess that image, initial guess as being white or whatever you want. If you many times say the new image is a quarter the old image to the right, up, left, down, minus the edge value, if you repeat that many times, you recover the image from the edges. That's not obvious at all. However, if you have a scientific or mathematical or engineering background, you will say, well, actually, you've defined the edge as being the second derivative of the image. We can undo that, okay, by solving this partial differential equation. Anyway, we repeat many times. In parallel, we must update the halo values for the neighbors every iteration. So this is analogous to the update equation in the traffic model. We're saying the new value is dependent on the old values of the neighbors, and we have to do it lots and lots of times. So we have to update the halo values every iteration, because on the next iteration, my neighbor will have updated his or her values of old. So we're going to do domain decomposition. And if I draw the image such that I goes, I'm going to say there's an M by N image. So I'm going to draw this so that I goes along and J goes up, okay, just to be contrary. In C, it's best to split the image into, as I've drawn it here, vertical slices, or split it in I, have every process have all the values of J for a subset of I. In Fortran, it's much simpler to do it this way, to split it up so that for every process has all the I values for some different values of J. Can anyone think there are two reasons why this is a sensible thing to do? You can do it the other way, but it makes life hard. There are two reasons why this is a sensible thing to do. There's a preferred direction of decomposition in terms cache currency, possibly, but that's quite a that may be true. That's a bit of a subtlety. Contiguous memory, yes, absolutely. But why is contiguous? You're absolutely right. So everyone's getting the right answer. This is related to the way. But why is contiguous memory useful here? So you're absolutely right. Having contiguous memory is useful, but there are two reasons. One is, yeah, do I have to use a defined data type for what? That you're absolutely on the right track. Lee is saying we don't have to use a defined data type. We don't have to use a defined data type for what part of the calculation or parts. I'm sure you've got the right answer. For set, absolutely. So in this example here, we're sending an entire line of pixels between process 0 and 1. If we decompose it in this way, those are lots of J values. It's image IJ plus 1, IJ plus 2, J plus 3, J plus. In C, that is a contiguous, as a lot of you have pointed out, that's a contiguous block of memory. So we can send and receive that data with a single message, but count n, okay? In Fortran, because it's the other way around, okay? In Fortran, it happens to be that in Fortran, arrays are contiguous in the first dimension I. So if we send a message that contains lots of I values for a fixed J, that is also a single message. So it allows us, now Lee was right, if we decomposed the Fortran version like this or the C version like this, we could have done that, but these boundaries would have been strided. We'd had to use a user-defined data type or something like a vector, which is a bit complicated. So the memory contiguity is the absolute key thing here. It impacts into the messages, but it also, it's maybe not obvious, impacts in the distribution and collection. If you distribute the data like this or like this, when I send the data out, I can distribute it with an MPI scatter, because a scatter takes a linear array and sends the first quarter to the first process, the second quarter to the second process. When viewed as a linear array, although it's a 2D array, that achieves exactly what we want with this decomposition. This block here is the first quarter of the array in memory or in Fortran. So the reason why it's worth doing this is it gives you two advantages, and as people have picked up, that's to do with the way a memory is laid out. It allows you to do the halo swapping with a single message of size M or N, but it also allows you to do the distribution and collection of the image, because we're going to nominate a boss process to read in the image using scatter and gather, because the first quarter of the image in memory goes to the first process, the second quarter goes to the second process. So is that clear? That's So what I provide you with is very detailed printing instructions, a tarball of CO Fortran with input routine, out routine, a couple of input files. I'm also going to give you the solutions because we have limited time. This isn't an extended like MSc semester course. My advice is that you write your own serial code with the halos for fixed bound and check that the serial code works. Now, it doesn't do actually distribute a serial code here if you want to look at that. I find that obviously writing a parallel program is tough, but actually the thing that people find tougher is actually working with somebody else's code. So you're welcome to take my serial code and work with it, but because it was written by me, not you, you might find that more difficult. Then you distribute the work. So I want you then to distribute the work onto the processes, but to do separate reconstructions. So what I want you to do initially is to distribute the work here, but do separate image reconstructions on each process without any halo swapping. So what will happen actually, it's an interesting thing to do. If I distribute a picture, give each process a single piece, and each of them does an image reconstruction, but they don't exchange halo data, and then I recompose the image, what do you think I see? You'll be able to do this in practice, but if I can guess what kind of thing you will see. But exactly, what you will actually see is an image with big lines across it. And this is why I like image processing examples for parallel programming. If you make a mistake, you see an artifact in the output which corresponds to something you did wrong. So when you do no image halo swapping or potentially incorrect halo swapping, you will see boundary effects, as Dale points out. Actually, what you see is big horizontal or vertical lines across your image. So that's interesting. And the further get the halos exchanged, and the way this program is written, this is unusual, but if you write the program correctly, you will get, because it's to do with it being the way it's slight subtlety of the way that the algorithm works, but your parallel code should give you identical answer in parallel to serial, bit identical. Okay. So if you want to view the images are in a very old-fashioned text-based format called Portable GrayMac. I like it because it's text-based. You can just write it, read them with printf or write. You should be able to view them directly from the EPC machines using the display program. It's such an old format that if you're working on your own laptop, it may not recognize them. So you may not be able to view these PGM files on your laptop. You can install the ImageMagick suite, which contains display, or you can convert them on an EPC system. So for example, the ImageMagick suite also contains conversion routines called if you convert image.pgm to image.png, you get a PNG file. So if you're running on your laptop, a Mac, or you may not be able to display these images. So you can either convert them on an EPC machine or download the ImageMagick suite. So I finally found, you should be able to see the course website. There we are. And so you can see here I have the case study exercise sheet, case study source code, which is just stub IO routines, which also case study solutions in serial in parallel. I've given COVID dynamic. I will cover technicalities to do with array allocation in C in the subsequent lecture. And I also given serial and parallel solutions to traffic model if you're interested. But what I'm interested here is the case study of the exercise sheet for the case study, sorry. The inline viewing in, it's not too bad in GitHub. So if I zoom in, whoops. So this just reiterates what, you can't see my cursor, reiterates what I covered before. It does an introduction, it introduces the method, again talking about the image, the algorithm we're going to implement. It shows you the results here. Now actually, what I wanted to, I do have a bit of time here. I will unfortunately this doesn't show up on this example here, but so actually if we zoom in on this image of Mel Gibson, you can see something interesting. Can anyone what do people see on that image? Might be slightly surprising. Square pattern, exactly. So I thought this was a bug, but it isn't. They are genuine. Now you can't really see them in the original image, but when you do edge detection, you can see square patterns. Can anyone know why it be? So I first saw, I said something weird going on here, and someone said, what format was that? I said it was a JPEG. Okay, so I downloaded a JPEG from the web of this image of Mel Gibson. Now JPEG uses Fourier compression. It basically takes the Fourier transform of the image and throws away the high frequencies. But it does the Fourier transforms in little, I think these are 16 by 16 pixel blocks. That JPEG image compression divides the image up into little blocks and does, to first approximation, a Fourier transform in each block. So the JPEG compression algorithm is lossy, and it does it in blocks. And if you do this image edge detection, you can see the edge artifacts, and those are artifacts from the compression algorithm, because the JPEG compression algorithm works on blocks of pixels. So that's not a bug. That was actually I was quite surprised at that. And they use this technique. There's a scam at the moment where you tell your insurance company you've had an accident, and you basically just Photoshop an image of your car to have a dent in it, hoping that they won't, this is of course illegal and you should never do it, hoping they won't notice, but they'll do things like look at the image. You can pick up whether people have messed around with images this way. Anyway, the serial code, all I actually provide you with the serial code are two routines, PGM and PGM write, in C or in Fortran in a routine called PGM-IO. I talk about viewing the edges. I give very explicit instructions here for the pseudocode for you to write your program. If you use the trick in Fortran that you're allowed to say where an array starts and stops, I would recommend, as you see at the top of the page here, that you make your arrays go from 0 to m plus 1 and 0 to n. So you want your arrays to be of size, for an m by n image, you want your arrays to be of size m plus 2 by n plus 2 because of the halo. If in Fortran you make your indices go from 0 to m plus 1, that means the Fortran and C arrays are almost identical, and therefore the pseudocode is almost identical for C and Fortran. So when I say loop from I equals 1 to m, I mean I equals 1 to m, j equals 1 to n in C and Fortran, because those are the core values excluding the halos. I want you to test it. Then I give you some hints for initial parallelization. The initial parallelization is to do distribution and collection of the image and image reconstruction, but without halo swapping. And then there's stuff to do halo swapping, and there's stuff to do with extra work. So that's basically it. Now we've been quite an intense morning. With the original schedule, okay, what we were going to do would have been to, if I go to, so you have access to that sheet. I've just stopped sharing it with the original schedule, which we're there would have been a long a break now, and then an hour and a half, and then a talk on designing MPI programs. However, I've slightly refactored that talk for this. It's now called Tips and Tricks. But what I thought was, with this. This is the way I run it in a physical classroom. But what I thought was that it might be better to reverse this slightly, to give you more time, leave the afternoon free. So what I'm going to try and set up so I'm asking you, I would like the schedule to be changed to have all the talks before lunchtime. If you could click yes or no, then I will, I've not done this works pretty well actually. There's a bit of peer pressure because you can see what other people are saying. But I can see that's a popular decision. Okay, fine. It's kind of unanimous. So, okay, fine. So that's what I will do is I will have a coffee break. I will give you some time to work with the case study, because some of the stuff I talk about in the tips and tricks requires you to have at least engaged with the case study and understood it. So what I'll do is I will take a break now. There will be a coffee break, but I will start the next lecture at midday and then finish by lunch. I want to give you a reasonable amount of time to assimilate. Ideally, you would have gone away and actually written this program, and that's clearly not possible in the compressed format and with doing it online. But I will. That was very useful. So what I will do is I'll put a slide up reiterating that, but that was the majority decision. So coffee break now. I will be back online at 11:30 to answer questions. It would be useful, I think, if you engaged with, looked at the case study, got it in your head what's going on. You can look at the solutions if you want. It's all up to you. But then I'll give the final lecture, which I've now renamed as Tips and Tricks, I think, rather than designing MPI programs, which I'll give that at midday. And then I will be around from 2 till 3:30, as indicated, to answer questions and such like, but all the lectures and stuff will be over by lunchtime. So I'm going to take a break now, and I'll maybe see you again, definitely at midday, but at 11:30.